Hi, this is Gary with Ballistic Recreations. There are a lot of videos on PIDs out there, but I think there is still something missing from the conversation, so here is my contribution. I'm going to make a disclosure. I do sell these things, so I have an interest in getting you interested, but I do promise to keep the salesmanship to a minimum in this video. If you've done much research on PIDs, you've undoubtedly been to forums where contributors there talk about the systems they have built and the applications they have put them to. You can go into any number of resources to find instructables on how to acquire the parts, how to wire them, assemble them, program them, and operate them. And it's certainly not hard to figure out where to buy the components. But what is missing is some discussion of rationale. Any heated system you're going to buy is going to come with some kind of a factory controller, usually a bimetallic thermostat on a dial or something similar. So why not just stick with that? What are the advantages of going to a PID, and is it worth the cost? I didn't have a well-documented and concrete response to that, so I decided I needed a test that could generate some data to show what are the advantages of a PID. I resolved to design a test program that could be duplicated easily, run it twice on the same system, once with the factory controller and once with an Autonix digital PID, to show what, if any, are the advantages of using a PID. A critical tool for this test would be this custom double PID controller that I built and do not offer for sale. It has an optional feature that allows it to communicate with a laptop computer. The computer collects the data throughout the test so that I can analyze it later. Through this test, I'm going to be controlling data on pot temperature on channel 2. Channel 1 is used to monitor the temperature of the bullet mold, which, while an interesting experiment in itself, is outside the scope of this test. After some consideration, I came up with the aspects that I thought should be involved in the test. I would test using a Lee Pro 420 lead pot and cast a bunch of bullets using a Lyman 358-477 two-cavity bullet mold. I would start with 4 kilograms of alloy in the lead pot with everything completely cold, and I would monitor it as it heated up to a set nominal temperature of about 400 Celsius degrees. I would put in a casting threshold so that whenever the time came to cast, I would start when the temperature achieved 390 degrees. First, I would do a run of 50 casting cycles. Since it's a two-cavity mold, I can expect to get 100 bullets out of that. For the first test, I would collect all the sprues in a container, and then when the first casting phase was over, dump all 50 back in. This would create a single modest temperature upset that I would monitor to see how the controllers responded. Once I was back up to casting temperature, I would do a second phase of another 50 casting cycles, identical to the first. Then I would take all the sprues that had been cut off, plus 2 kilograms of cold ingots, and put them in the pot all at once. This would create a major temperature upset, and I could watch how the controllers responded to it. Now this number, 2,000 grams, is chosen for a reason. Since at this point I've cast 200 bullets and they weigh about 10 grams each, putting 2 kilograms back into the pot at this point really takes me back up to the level I started with. Once the temperature was fully recovered from the major upset, I would do a final casting phase, this time 100 casting cycles for 200 bullets. But this time I would be returning the sprues to the pot after every 5th cast. So that would give me 20 minor temperature upsets throughout the course of testing. I figured that these elements would give me a very good look at what the controller was capable of as it heated the pot up, maintained it through casting, and then responded to various upsets along the way. With the test program decided, obviously there was not much to do except get to it. So with the test complete, let's take a look at the results. Now with all these time temperature graphs that I am about to show, they have some similar layout. You will see elapsed time along the bottom here in minutes. Pot temperature in degrees Celsius is displayed along the left-hand side. And they all have this dotted line displayed at the 390 degree level. This shows my casting threshold. So anytime my temperature gets above that as the pot heats, I feel it's okay to start casting. And of course we have these two colored trace lines. The green line shows the time temperature path of the factory dial thermostat, while the blue line shows the performance of the PID controller when it was running the pot. So this is the initial warm-up phase. We turn the pots on at about 1 minute in, and we see heating very, very similar in terms of slope as they rise up until we hit the melting point. At the melting point, we get some slowing down. This is to be expected because the heat that is flowing into the pot is going to melt material rather than to raise the temperature. But it really seems to impede the dial control once we hit this phase. Coming out of it, we see our slope has changed. Clearly what's happening is the controller is sensing that it's getting very close to its set point, so it is slowing down as it sneaks up on it. The PID sort of powers through the melting phase and then resumes the heating cycle at a slope similar to what we saw down here. So it ends up getting to the casting threshold much more quickly. By the time all is said and done, total time for this phase is 19 minutes for the PID controller and 30 minutes for the factory controller. Once the pot temperature has crossed our 390 degree threshold line, I begin casting. The performance of the factory dial controller, it continues upwards towards its nominal set point, which turns out to be about 411 degrees. It peaks there after a few minutes and then does start to drop slowly, although it has not dropped even to as low as my 400 degree nominal by the time I'm done casting my 50 casts, my 100 bullets. The PID controller, on the other hand, it rises to 400 and then basically flatlines. We see a couple of short bobbles in temperature here of a degree or two that last a few seconds. Apart from that, it sticks on the 400 degree line right up until I finish casting and dump in the next phase. So time to do this portion very similar between the two at 18 minutes for both of them, which shows that I'm able to maintain a consistent pace of casting even though these two tests were done on different days. The next phase of our controller test is the minor upset. So I take all the sprues that were collected in that first casting phase and I dump them into the pot all at once. And you can see that both pots initially respond very similarly. They're up around 400 degrees and they plummet very quickly down towards about 350. Once down there, the factory, you start to see the difference. The factory controller takes about a minute to respond, and then it applies a certain percentage of power, resulting in a increasing heat at a steady rate up until we get back to the casting threshold at a time of about 9.5 minutes after the sprues were dumped in. The PID controller, much more aggressive. Looks like it might be recognizing the problem while the temperature is still falling. We start to see perhaps the power comes on here because the slope changes. It doesn't cool down quite as far. It doesn't sit down at that bottom temperature nearly as long, and then it comes up much more sharply so that we're actually back and ready to cast well short of the 3-minute mark. With our temperature fully recovered from the upset, I do a second session of 50 castings. Very similar. This is essentially the same thing that we saw in the first one. Just 50 casts collecting the sprues off to the side. And we see the same type of performance. The factory dial controller continues on up, peaks, and then starts to drop down. And this time it actually drops down below my casting threshold right around the time that I'm finishing up. If I had kept on, it's difficult to say, but it really does look like it would have fallen somewhat. We don't know how much. It would take a longer session to figure that out. But this is a sign that with longer runs, the factory dial controller might allow a lot of drift on the temperature. The PID controller, on the other hand, similar performance to what we saw last time, spends most of its time right at 400 degrees, couple of excursions 2, maybe 3 degrees lower than that. In terms of time, the tests are very similar to what we saw in the first session of 50 castings, 17 minutes with the factory controller to do the 50 casts. For some reason, I took a couple of minutes longer with the PID. It doesn't seem to be related to temperature. I don't recall what exactly I was doing, but I'm guessing that something was in my way or some external issue I had to attend to that kept me from starting for a couple minutes. Because otherwise, this is the only period out of the 6 casting phases with the 2 tests. This is the only time I really break pace, and I really don't recall why, but it really does not have anything to do with the controllers. Now for the big one, this is the major temperature upset. I return all the sprues from the previous casting phase into the pot, plus I throw in 2 kilograms of fresh cold lead alloy. The result on the pot temperature is very dramatic. Both of them plummet right down, and we see to about the melting point of the alloy. It looks here like in the factory pot it has frozen. Probably in both pots we did see solidification for at least a portion of time. Really, really remarkable how much this throws the factory controller for a loop. It takes 20 minutes of reheating before it can remelt all of that material, and we start to see a rise in temperature again. Even when we do see a rise, it's a partial application of power, and it starts to taper off as it rises. Clearly, the controller is trying not to overshoot by sneaking up on the temperature again. But boy, does it result in an extended recovery time. Looks like it's 37 minutes from when I add the ingots to when I am back and ready to cast. The PID controller has none of that issue. It does drop down. It takes it only about a minute to remelt the material, and then puts the heating cycle on at full power. Temperature increases back up, ready to cast in 9 minutes. A very remarkable difference. And it needs to be pointed out just how slow this factory controller is here. If you recall our initial warm-up, 4 kilograms of cold material in a cold pot only took 30 minutes. For some reason, this type of upset fools the controller into only applying partial power, so it takes longer to recover from this little upset than it took to heat the pot in the first place. This brings us to our final casting phase. This is 100 casts continuously, except that I return the sprues to the pot on every 5th cast. So we have 20 small additions that upset the temperature of the pot along the casting way. And here we can see the controller, of course, as we saw previously, tends to overshoot. It looks like the overshoot tendency combined with the cold alloy being dribbled back in resulted in a flat line for close to 10 minutes as they canceled each other out. But after that, the regular additions overwhelm the controller, and we get a steady decline of temperature throughout the test, increasing as the pot gets emptied. The PID controller really doesn't have much of an issue. It does dip quite a bit, a good 10 or 12 degrees on about probably the second addition. Then it recognizes that this upset is becoming more severe, so it applies more power. And once it has matched the power input to the cooling effect of the additions, then all we see is these neat little oscillations within a very tight range of about 4 degrees. And in the vast majority of cases, I dump in the sprues, and then the pot has rebounded to the set temperature before I'm ready to dump the sprues in again. We're back on pace with this phase of the casting session. Times are almost identical at 37 minutes for the PID, 38 minutes for the factory controller. But if the session was to go on much longer, I would have had to pause because I was just starting to get too far out of my acceptable temperature range. So let's summarize by putting all of that onto a single chart. We had an initial warm-up period. Took 19 minutes for the PID, 30 minutes for a factory controller. This was followed by a session of 50 casting cycles, which virtually identical for the two at about 18 minutes apiece. Then came our minor upset. The PID controller recovered very quickly in 3 minutes, while the factory dial controller took 10. 2 more. Then came another casting phase for each of the cycles. They were again very similar at 17 and 20 minutes, with the factory dial being credited with going a little faster, whether or not that's true. Next came the major upset. This was the big event of the casting. test. 9 minutes the PID recovered from, while the factory dial thermostat required 37 minutes to recover from this temperature dip and get us back up and casting. Then our final casting phase, very similar in length at 37 and 38 minutes. Some suggestion here that the factory dial thermostat would have eventually caused quality problems as we were just drifting steadily, and eventually we're going to very soon go out of acceptable casting range. Final result, both tests produced 400 bullets, but when casting with the factory thermostat, it took us 150 minutes to get there versus 106 minutes when running a PID. So this really does, I think, show concretely what the advantage is in having a PID. Primarily, it's about time management. The casting sessions were the same length, but heating times in all three phases where we were applying the PID brought the pot up to temperature much more quickly. There's also some indication that we would eventually get casting quality problems with the factory dial with just too much drift. Didn't really affect us making 400 bullets, but it would in longer casting sessions. So I hope this has been of some use to those of you who are trying to figure out whether or not you need a PID for your system. If you do, I hope you look at the Ballistic Recreations unit. Bye for now.